This is a short. I'm Claude Coulombe. This is a short presentation. I will share with you some of my experiment work about solving a practical problem I came up against. There is a price to pay for deep learning, and it's the amount, the huge amount of data we need to train those models. Deep learning needs huge data sets, and we have to find solutions to get across the big data wall, particularly for natural language application. This big data wall represents a challenge for minority language, communities on the web, organizations, laboratories, and many companies, startups that compete with the giants of the GAFAM. That said, the need for a large amount of data is not specific to deep learning. In fact, it's related to the complexity of the task we have to solve. Then there is some rule of thumb about the amount of data for deep learning. It needs about 5,000 labeled data examples per target class to train a model able to achieve acceptable performance, and millions of examples to exceed the human performance. To get across this big data wall, many solutions exist. The most popular one is the transfer learning, but we still need large amount of specific data to train for a specific task. That's where data augmentation can come to help. By habit, we say data augmentation, but it's rather data amplification, because we use existing data to create new ones while preserving the meaning of the sentence, of the text. So the idea of semantically invariant transformation is at the heart of the data augmentation in natural language. Data augmentation also refers to synthetic data, generated data, artificial data, or sometimes fake data. In computer vision, it's common practice to create a new image by geometric transformation that preserve similarity. This type of data augmentation was used to win the ImageNet challenge in 2012, which marks a turning point for deep learning. In speech recognition, data augmentation is achieved by manipulating the signal and by noise injection. Speaking of text data augmentation, or TDA, it's still uncommon. Until recently, the only widespread TDA technique was lexical substitution, which consists of replacing a word with its synonym using a thesaurus. But it's no secret that hand-coded rules, including noise injection, are also used. My research goal was to study the feasibility of TDA techniques, mainly at the pre-processing level, that are practical, robust, and simple to implement. Some existing TDA techniques have been tested for comparison, such as noise injection or the use of regex, regular expression. Others have been modified or improved, like lexical substitution. Finally, more innovative TDA techniques have been tested, such as generation of paraphrases, to back translation, and syntactic tree transformations using practical, robust, and easy-to-use online services. Some general guidelines rules to preserve, mainly to preserve the meaning, the semantic. First, the rule of statistical distribution, which states that the augmented data must follow statistically the distribution of the original data. Second, the golden rules of plausibility. So a human being should not be able to distinguish between the augmented data and the original data. Third, the semantic invariance rule, which states that data augmentation involves semantically invariant transformations. A very simple TDA technique is textual noise injection, which consists to remove, replace, or add at random characters or sequence. A very similar technique is the misspelling error injection. Then the classical lexical substitution using thesaurus, which consists in proposing words, typically synonyms, coming from a thesaurus, like WordNet, that can replace a given word. I've experimented use of word embeddings or word vectors to improve this TDA technique, particularly a technique that able to process polysemous word vectors. More interesting are the paraphrase generation techniques, although they were considered unrealistic by some. Then we have the definition of the perfect data paraphrase, is meaning preserving and must also diverge as sharply as possible from the original sentence. So it's a difficult task. For example, surface transformation using regular expression. Good start because they are simple and very efficient in terms of computation. More interesting is paraphrase generation using syntax tree transformation. This technique was inspired by work from Michel Gagnon, Polytechnique Montréal. The idea is to transform, to change the syntactic parsing tree of a sentence. Each sentence is submitted to the SyntaxNet analyzer, which is based on deep learning techniques and the TensorFlow library. The code is executed in Google Cloud infrastructure using the Cloud Natural Language API, and it's very cheap. The transformation rules have been built manually according to the paraphrase typology of Villa, Marti, and Rodriguez under the 2080 Pareto's engineering principle. Marie Bourdon, computer linguist at Cogenev Montreal, provided valuable assistance to this work. Now, very interesting and more use is paraphrase generation using back translation. The idea started with a discussion in the hallway with my old friend, the physicist Antoine Saucier at Polytechnique Montreal at the beginning of 2015. The idea was in the air. The first mention of back translation to introduce variants into text data under the term round-trip machine translation can be found in an article published by a team from King's College London, presented in a 2015 conference. Back translation is an old trick used to test the quality of machine translation. In fact, for a given sentence, there are generally a lot of equivalent correct translation because the huge combinatorial productivity of the natural language. By definition, all these equivalent translations are paraphrases. Each original sentence is translated using Google Translate API, which is a neural machine translation system. A second translation call produces the back translation. Then back translated potential paraphrases are filtered using different mechanisms to be retained or discarded. For the filtering based on we use similarity, we opt for a simple difference in length between the back translation and the original text, but we also use a bleu metric and a logistic model trained on manual labeled data. To experiment the different TDA techniques, we choose a simple problem, the polarity prediction, positive or negative of movie reviews. a standard data set, the EMDB database, and common deep neural network architectures. This will make it easier to isolate the effect of TDA. The experiment is divided in 2 phases. First, a preprocessing phase where the text data augmentation is performed using different techniques. And second, the training phase of different neural network architecture on the original data and the amplified data. Then the models are compared to see if there is any improvement or degradation in the performance of the model in terms of prediction, accuracy, training errors, and if one measurement were also performed. Given scarce computing resources, we have limited our experiment to proof of concept only. Much work remains to be done to explore each TDA techniques in detail. The neural network architectures, nothing very exotic, classical feed-forward network, multi-layer perceptron, some convolutional net, CNN 1D, and 2 recurrent network, LSTM and BLSTM. Here we can see the results. You have the baseline, the accuracy without any data augmentation, and the accuracies with different TDA techniques and error bars. So it works. Good news, all the TDA techniques improve the accuracy in a range from 4% to 20%. I've also tested with classical XGBoost algorithm with little improvement, about 2%, but also a degradation with more amplified data. We can see that accumulating many TDA techniques seem to get greater improvement. The result for CNN, there is a lot of variability with CNN, probably due to the deep of the networks. The result for the LSTM, we can see that when we add different data set, augmented data set, there is an improvement in the accuracy. Same thing for the BLSTM, but BLSTM and LSTM were very, very long to train, many days. The main advantages of the proposed TDA techniques are from practical and software engineering point of view. Leveraging online NLP service of established suppliers offers many concrete and immediate benefits: availability, robustness, reliability, scalability. In addition, there are inexpensive, ready-to-use solutions available in a large number of languages. The main drawback of some of the proposed TDA techniques are the large amount of computation. In general, TDA techniques based on syntactic tree transformation and back translations degrade with the length of the sentence processing. Some of the proposed TDA techniques rely on commercial NLP online services that come from private providers introducing a dependency. The proposed TDA techniques have advantages over emerging approach like textual GAN, that they do not seek to generate sentences from scratch as GAN does, but rather to leverage existing already meaningful sentence, the sentence with a fixed meaning, and using semantically invariant transformation, we can preserve the semantics. Other techniques require mastery of cooking of neural networks. So, GAN are very unstable, difficult to train. They also involve very long and tedious calculation. Finally, the TDA techniques proposed in this study are similar to those already used in computer vision. The main limits of this work is that the experiment was done only on a single task, and it's also a very simple one. In conclusion, this empirical work, more engineering than science, conducted with limited computer resource, has shown different text data augmentation techniques that are simple, practical, and easy to implement. Much work remains to be done to explore each TDA technique in more detail. Finally, the simulation work is needed to introduce these techniques to practitioners, engineers, researchers who are seeking concrete and practical solutions to overcome the big data wall in the application of deep learning to NLP. Thank you.
Definition of semantic invariance. I can understand what a phase invariance or engagement invariance or topological invariance. Do you have a rigorous, maybe you can refer me some papers, definition of semantic invariance? Same thing for computer vision.
Yeah.
Is it the equivalent of adding a phase and then averaging over an ensemble, or is there some sort of other analogy that you can?
The idea behind is to have semantic and invariant transformation. So we start with a meaningful sentence, and we change it in respect of the semantics. So if I take a phrase, a sentence, and I go to the passive form, so I didn't change the meaning of the sentence, but the structure, and it looks very different. And also, back translation is a good techniques, because when we translate, we respect, we keep the meaning. So if you have many different translation of the same sentence, it should be, in most cases, it's a good paraphrase of the sentence. So it's the main idea.
Can semantic invariance be quantified? That's what I'm looking for. Quantifiable. Can you calculate the invariance?
It's difficult to quantify semantics. So we can evaluate with maybe people if we tag and annotate the corpus, and it's possible to have to measure by using human as the reference. Yeah, it's possible. As in translation, it is like that. So we use a blue translation, blue matrix. So you can put good and human translated references in blue to be able to compare with the reference coming from a human translator. So we can do the same for that kind of transformation. Yeah, could be done, but we need to have data from tagged data from human.
Thank you.
Any other question? Maybe just the last one.
I'm not really sure I know what exactly back translation is. Is it like translating from, let's say, English to
Someone,
French and then
yeah.
French back to
Yeah.
English?
Yeah.
Okay, so what about, is this the one that I'm going to say, is it also back translation? So, for instance, English to French and then Spanish and then back to English?
Yeah, you could do that, but when it's the problem of the Arab phone, when we have many people in the chain, and sometimes you lose the meaning. Yeah, and there's some tests, some evaluation about the longer of the length. The length of the path between each steps of transformation. Yeah.
Okay, thanks so much for that.
Thank you.